So here, notice that the top 5 error is used, which means that the correct answer should be around amongst the top 5 predictions of the classifier. And basically, what AlexNet did was to start a trend or start a movement for using convolutional neural networks in image analysis and vision tasks. So AlexNet was inspired by the LeNet convolutional architecture. It was designed by the team of Geoffrey Hinton, and basically it helped to revolutionize the field of computer vision by being at the forefront of many, a lot of different ideas that started to emerge after this work. So it followed the same principles as LeNet, but it was much larger than that network. And it basically had 2 different paths. It had 7 layers instead of 5 in LeNet. And it had 1 million. They also added some dense layers at the end. Another thing that they introduced in this paper was dropout, which we'll see in the later slides, which is a technique for regularization. So how AlexNet worked was that it employed a bunch of tricks in order to reach such high levels of accuracy. So first, it processed different crops from the same image. And for each one, it extracted a feature vector after the last convolutional, the last dense layer. And then it flipped the image and extracted different crops of the from that image. Then they averaged the feature vectors and then passed it through a softmax layer for the prediction. So that was AlexNet, the first network that demonstrated the use of convolutional neural networks in large-scale image recognition challenges, and it basically took everyone by surprise, because at that time no one thought that it was possible to train neural networks without overfitting on that large scale with large-scale data. So as a consequence, after that, a lot of people started to look at convolutional neural networks. And in the second year, and the next year, actually, the winner was also a convolutional neural network, which was basically using similar ideas, but with some minor improvements. And in the next year, in 2014, another important milestone entered the competition, the VGGNet, which was from the Oxford Visual Geometry Group. That's where the name comes from, VGG. And they tried different configurations, and their best model was able to almost half the error of the previous year. However, at this year, it only took the second place, and we will see the winner in the next few slides. So the basic ideas that was proposed by VGG was that they rather focused on making the network more modular, because AlexNet used a lot of different sizes of filters, like 11 by 11, 7 by 7. So the effort here was to make a more modular network. and replace the larger filter sizes with 3x3 filters that are used. This was able to reduce the number of parameters. So one 7x7 convolutional layer requires much more parameters than having two successive 3x3 layers. And they also did some experiments with 1x1 convolutions to further reduce the parameters. And you can see here on the left the different configurations that they tried. So their approach was to build small blocks of convolution layers, followed by max pooling layers, and then use fully connected layers in the same way that AlexNet did. So effectively, they increased the depth of the network. And the strategy that they followed was after every pooling layer, which basically means that they reduced the spatial resolution, they doubled the number of filters in the next layer. However, one major drawback of this is that by the end, where we reach the fully connected layers, basically at that point, you have to flatten the feature map to make it into a vector. They had a lot of parameters that had to go into those two layers. And also, as you increase in this way the depth of the network, then your parameter count keeps increasing. So in the same year, actually, the winner at that year was a work by Google that participated with an architecture called GoogleNet, in reference to the LeNet architecture. And they proposed a different approach in order to make the networks. So they proposed the Inception layer, since Inception refers to the fact they have a smaller network within the convolutional network. So the Inception module basically uses convolutions of different sizes and different types. So they have a 5x5 convolution, a 1x1 convolution, a 3x3 convolution. And the idea behind this is that we don't know beforehand which of these convolutions are useful. So instead of having at a layer only 3x3 filters, you have you also have 3x3, 5x5, 1x1. And you can apply these in parallel and get different feature maps and basically make a combination of these feature maps by stacking them one after the other. And it's up to the network then to find which of these convolutions and which of these operations it finds useful by setting the appropriate weights in the subsequent layers. So they also added some 1x1 convolutions, where they basically reduce the spatial resolution so that the computation becomes more efficient. And they call this the bottleneck layer. And now this layer, the bottleneck idea, is also used in other papers and other works. And this is the GoogleNet architecture, how it looks like. So as you can see, it's not as modular as the VGG network. It has some normal convolution layers at the initial stages, and then it has Inception module, which is comprised of the different types of convolutions, some bottleneck layers, and then these are concatenated along the channel axis to form a bigger feature map, and that feature map is then propagated to the next layer. Another innovation that they tried in this work was to add, as you can see here, in the outputs, we have 3 different classifiers. So they added auxiliary classification layers. So they had a small number of layers after at some point in the network. And the main reason for that was that as you go deeper into the network, it becomes more difficult to train because of the vanishing gradient problem. So as you recall from the previous class, the gradient, as it flows backwards, we multiply it with some small learning rate. And as we go backwards and backwards, that value becomes smaller and smaller. So at one point, it becomes so small that it is very difficult to update the weights. So by adding these auxiliary classifiers, what they were able to achieve was to allow some gradient information to flow earlier from earlier parts of the network. So here we have basically 3 different losses. It's the same type of loss, but it's 3 of them, and their combination gives the final outcome. And in this way, they were able to train this deeper model. So this is an overview of the different architectural parameters in GoogleNet, and it achieved an error of 6.6%. And as I said, it won the ImageNet challenge that year. They also proposed in later versions some additional improvements to the Inception model to make it more efficient. So they used a technique called batch normalization for training, and which we will see in the later slides. Of the auxiliary classifiers, but factorize. So basically, that means that they approximate convolutions with the succession of smaller convolutions, which are reduce the complexity in the number of parameters. And at the same time as Google were trying to improve their Inception, the he and different and they basically evaluated themselves on the data set. By achieving an error rate of 5.1%. That was basically 1% better than what GoogleNet was doing. So this set a benchmark for the human performance in the ImageNet challenge. So this was the leaderboard at that time. Since AlexNet was proposed, the error rate dropped significantly. And the trend was that people were going deeper and deeper in terms of adding number of layers. However, the problem at the time was that by increasing the number of layers, it was becoming more difficult to train neural networks, primarily because of the vanishing gradient problem. So in the next year, in 2015, the winner was ResNet, which actually tried to tackle exactly that problem, the problem of vanishing gradients, through something called skip connection. And what they wanted to do was to increase the number of layers arbitrarily without having the vanishing gradient problems. So some remarks before we go into what they actually proposed. This was a network that was trained for over 2 weeks on 8 GPU machines. And at runtime, it was much faster than the VGG, even though it had many more layers. And interestingly, it not only won the classification track, but it also won other vision tracks like detection and segmentation. So it showed that their approach was rather general and produced really good results. So their main revolution was the increasing depth of the network. So as you can see here, we went from 19 and 20 something layers in GoogleNet into over 100 layers in ResNet. And ResNet is short for a residual network. And this is basically what they propose. They propose having residual connections in the network. And their idea was that as we increase the number of layers in the network, what we're doing basically is we're changing that network can be approximated. But we don't want to change the number of functions that the network can approximate. What we want to do is expand the functions that types of functions and may and to do the if 0, you are basically getting the ID basically. So this means that the benefit of this is that it's guaranteed that it will not hurt performance, because you always there's a way for the network to recover the input. So any new layer you add, the network can choose to ignore it by just setting those weights to 0. And this is an expansion of their residual module. And this is basically employs the bottleneck layer that was introduced in Inception by first reducing the size for channels, then doing some convolution for feature extraction, and then expanding back to 256 so that it matches the input, and then you add the input to that layer. And this results in significant reduction in number of parameters. So there are different versions of ResNet. Some of them are available in the deep learning frameworks. And each of them differs in the number of layers that you have in the network. And if I recall correctly, I think they also trained even a 1,000-layer network. So they showed that it is possible to go really deep. Now the performance does not increase dramatically, but by adding residual networks and residual connections to any network helps to at least add more layers without affecting the performance. So this revolution in depth was able to beat human level performance. So whenever you see the headlines for this classification challenge that convolutional neural network beat the human performance, they basically mean that they beat the performance set by Andrew Karpathy in this data set, which was around 5%, and now ResNet dropped it down to 3%. And it basically shows that if you look closely, they more than doubled the number of layers, dramatically more, and the performance they got was not was around half, more than half in terms of reduction. So it's not proportional to the number of layers. So the way the researchers tried to interpret ResNets was that they act as a collection of many different paths, and by allowing the network to choose the right paths, then it's able to train much deeper networks and much more efficiently. So in this diagram, say you can see how some prediction at the end of the network can be moved directly to the first layer. So later on, inspired by this idea, the researchers at Google, of course, added a skip connection to their Inception module. And it was the Inception version 4 paper. And they also showed that residual connections do help even in their own network. So this is the complete picture of the ImageNet challenge that between 2012 and 2015. As you can see, the error was dramatically reduced since the beginning. Now people use it for benchmarking, but the challenge is no more active. So one other thing to see here is that some entries used the whole ImageNet dataset as external data to achieve a better performance, whereas the latest versions they showed basically that their own architecture was much more efficient in extracting more meaningful features from a smaller data set, since they did not use any external data. And today there are other techniques that can go even lower than these results. But people are discussing whether or not this is just this is useful, getting much lower on this particular data set. So as I said, people have continued to work on ImageNet, and it's used in research to compare different algorithms as a benchmark. But there are many different tricks that people did not pay much attention to in these papers. So, for example, the fact that the AlexNet used the different crops, they flipped the image to achieve such a high performance. In addition to that, different training strategies that people could use, whether or not they average different classifier outputs, like the different auxiliary classifiers, or some other have used ensembles of networks, so not just one neural network, but many neural networks. And these are all different things you can do to boost your accuracy, basically. So let's talk a bit about some training strategies when working with convolutional neural networks. So in essence, they're not so different in terms of training with respect to the dense layers. We do, however, have some more tools that we can use, some advanced regularization techniques that can help us combat overfitting. And we can, of course, still use all the different tricks that we had and regularization techniques that we have with the standard dense layer networks. In essence, we use stochastic gradient descent. So we have a batch size that we update the weights on, and we do that with backpropagation using the different optimizers that are available, like ADA, gradient descent with momentum. In addition to that, what we want to do, since people have started to use deeper and deeper networks, and this means that the parameters increase dramatically, we want to combat overfitting. So to do that, some of the more, let's say, popular approaches are data augmentation, dropout, and batch normalization. So data augmentation basically is a technique that artificially generates new images from our data set. And it does that by creating modified versions of the images that we have in the data set. And it helps to combat overfitting. So we create these images by applying different transformations on the source image. So we could flip the image, we could rotate it, change the color distribution, the brightness. We can also crop a part of the image, zoom. We could make the image smaller and add some black borders around it, so we reduce the size of the object. But of course, whenever we apply these transformations, it's important to not do it in a way that distorts our objects and changes dramatically the appearance of the objects. So recently, there have been some methods that basically use other neural networks to learn better data augmentation strategies. So they have neural networks generating themselves augmented images of our source data. Another regularization technique is called dropout. So it basically involves, as the name suggests, dropping out units from our neural network during the training. And by dropping out units, we mean that we set their output basically to 0. And this means that we don't take them into consideration when we compute the loss and backpropagate the error and update. So in essence, as you see in the image there, is that at every iteration, we use a smaller subset of the neural network to do training. So as a result, the units learn to rely not only on one specific neuron in the previous layer, but at various different neurons, and which can change over time. And as you see on the figure on the right, the classification error with Robot can go significantly lower because our network doesn't learn or to rely on some specific neurons, but rather the information and the ways that it tries to classify images changes over time. So it has to adapt accordingly, leading to better performance. So we usually apply the dropout layer after at one of the output feature maps. So after we have the convolution, we have the activation map, and we can apply it there, or after a pooling layer. And we usually specify a probability by which some of the neurons are respectively. So you can apply at dense layers because they have the most number of parameters. So another a very popular technique for regularization is called batch normalization, and it's a technique to improve the speed and the performance. And it was initially motivated by the internal covariance shift. This probably refers to cases where, since we are working on batch, some batch may drive some neuron outputs to have some particular values, another batch can change those values, and altogether these neurons have a different distribution of their output depending on what the input is. Combat this. So they devised a way so that after every layer we can adjust the values of the output so that they have a zero mean and unit variance. So they do that by gathering some statistics on the batch, so the mean of the batch and the variance of the batch, and they basically transform the output of a layer to update the weights, and then they added some scaling factor gamma and some bias B to perform shifting, and that value goes to the next layer. So the effect of the batch normalization is evident from many different works. However, there is still a discussion on whether actually, if batch normalization actually helps combat the internal covariance shift, or if it just adds noise to the layers so that it basically acts as a form of regularizer. But even though this is open for debate, the effects that it has is profound, and it's basically used in many different architectures. So in general, besides these normalization techniques and regularization techniques, we also use some techniques to make our networks more efficient in terms of computation and more parameter efficient. So generally, reducing the filter size helps in having less parameters. Also, factorizing the filters helps a lot. We didn't go into detail in this, but the idea is that if you have a 3x3 filter, you can approximate that by applying one 1x3 filter first, and then applying a 3x1 filter. We use one-by-one convolutions to reduce the number of feature maps before we make some expensive convolutions at subsequent layers. Minimizing the reliance of fully connected layers also helps reduce the number of parameters. We could want to also reduce the spatial resolution gradually, not too early, where features where semantic information has not been formed yet, but not too late, so that we process high resolution feature maps. We want to use skip connections to help with the gradient flow, and generally, if we in the network, it helps to also consider features at different levels, and all this involves a trade-off between the depth, the number of layers, the width, which is the number of filters in a layer, and the cardinality, which refers to the number of the different paths we can have in the network. So generally, we do not guarantee to converge to zero during training, and we may converge to a local optima, but using the techniques that we saw can help into avoiding this. And generally, when we have a large network, it converges to some error, low error. It could take thousands of epochs to converge, but batch normalization can help to reduce that. It helps to run different trials with different starting points, so that we start from a different point, the loss function in the loss function plane. In setting the learning rate could be difficult, but there are a number of strategies for that, like, for example, starting with a high learning rate and then reduce it after a few epochs if performance is not improving. And basically remembering that neural networks are still similar to what they were a few years ago, and we can use a vast array of tools to train them with some approaches that we had before, and also with new, like dropout. So in general, neural networks, we have to train them for a lot of epochs in order to converge. But this could also result in overfitting. We need to identify that, and we do that by holding out the part of the data that we don't use for training, but just use it for validation purposes to see if our performance is similar in these two data splits. And when it starts to converge, then it means that our training data, the network overfits on the training data, because it tries to discriminate the training data with features that may not be present in the test set. So it's always a good practice to have validations data on the side. So some best practices, using a mini batch it helps to converge faster rather than using stochastic gradient descent. Using regularization like L1 and L2, as well as dropout, helps. When we develop new functionality, it's important to use gradient checks to see whether or not something in the network does not permit a gradient to flow backwards. Using cross-validation to catch overfitting. Nowadays, people use ReLU or a version of ReLU instead of a more traditional sigmoid function. Centering our data around 0 always helps. Initializing with the Javier initialization, which takes into consideration the fan-in of each node, is also helpful. And the learning rate training a scheduler can also improve performance. Another thing with regards to the efficiency of neural networks is the fact that we can basically do away with the fully connected parts, and we can show that a fully connected layer is basically a dense a convolutional layer with one-by-one convolutions. So by doing just that substitution, it allows us to have an expandable layer so that our output changes according to the resolution of our input. So in this case, in the bottom figure, our network basically, because it takes a much larger image, outputs an array as an output, and at each position of the array, we can view it as a class of that particular crop of image that it processed. And this is done automatically if we just substitute the fully connected layers with the convolutional layers. And this is an approach that, as we will see in the next lectures, is used in detection as well as segmentation. To use lots of data. We will see. Since we can utilize what is called as transfer learning. We basically want to transfer all the knowledge that is acquired by neural networks like VGG and ResNet and so on into other tasks. So it turns out that these networks that are trained on ImageNet and are available provide an excellent feature extractor. So the idea here is to take such a network and then repurpose it for a different task, like, for example, medical imaging. Let's see how we can when we have more data, we usually need more weights to train on. So deeper networks need more data. On the other hand, if we use less weights for a network, this that may not help the network to achieve a good performance. We can exploit this in the following way. So we can have the weights learned from another network, and we basically only retrain or learn the latter parts of the network. So using ImageNet as an example, when we have a network trained on ImageNet, it learns features that can be used across different image domains. So what we do is we basically take observations from the fully connected layer, and we treat that as a feature. Then we can add either another fully connected layer or another classification algorithm and train for our own data set. So it's basically where we leave some of the weight of the previous network untouched, or we just change them slightly. Is called fine-tuning. So in a general framework for transfer learning, we source task, for example, ImageNet. We could, with its own labels, we train a neural network with some convolutional and some fully connected layers. And then we basically take these weights and these parameters, we copy them into another network. We cut some of the last part of the network. We add our own classifiers on top of that and train for our own data set. So here, for example, we have a network trained on ImageNet. If we have a small data set, then we could remove the softmax classifier and one of the fully connected layers. We freeze the rest of the network so it doesn't change its weights. And we add on top another classifier and we train on that. If we have a rather larger size network data set, we could also remove some additional layers from the top of the network. And this is usually done because the representation that is learned at the very early layers is more generic than what is learned at the top. And also we could have any classifier. We could add another softmax layer, or we could use SVMs as our classifier. So this is a general strategy for selecting. It's not a concrete strategy, but it gives you an idea on how you could possibly said at the beginning we have more generic features, so they could potentially be used for many different applications. And as we go deeper into the network, we have more generic, more specific layers that correspond to the classes in the source data set. So if we have a similar data set but very small data, we could use a linear classifier on top. If we have a very different data set and very little data, then it might not be possible to use transfer learning at all. Maybe probably only the very early stages. If we have lots of data and a very similar data set, then we could fine-tune some of the layers. And as if we have a much different data set, then we need to fine-tune more of the top layers. Cases detection or caption. For example, they use it to extract some features, and then they produce text that describes what's in the image. And in both cases, they use some pre-trained networks on ImageNet. And today, this approach is somewhat standard across many different domains. For example, I was reading that Facebook uses a billion images to train general feature extractions, which later they take and they cut some layers and they put their own classifier or some other task-specific layer, and they use that as a backbone to train on the new task. So it's a process that, especially for industry where they are just interested in making something work, it's really popular. So in general, what are convolutional neural nets good for, and what are the applications that can better utilize them? They can be used, and I refer here to signals because they are more general than images, but it applies to images as well. In the signals that come in the form of multidimensional arrays that have some local correlations, where some features can appear anywhere in that signal, the same features, and where objects are invariant to translations and distortions. So we can use one-dimensional convolutional networks when we have sequential signals like text, for example, or some acoustic signals, or some time series prediction. We use two-dimensional convolutional networks, which is what we saw in this lecture, when we have images, or some time frequency representation, like for speech and audio, to do tasks like detection, localization, and recognition. And we can also use 3D convolutional neural networks whenever we have 3D data, like, for example, video. If you consider a video as a sequence of frames, that is a 3D data structure. Whenever we have volumetric images, or for example, tomography images, 3D graphs are also an example that fits into this. And again, we have similar tasks like recognition and understanding. There are different numerous resources that you can go on and look and find more material. I just put some here for your reference, but a Google search you will find many more. These are also some papers from the topics that we covered today. They basically set the cornerstone for modern deep learning research in computer vision, and would encourage you to have a look at them. So in closing, today we saw an overview of how we moved away from perception and multi-layer neural networks and into convolutional neural networks that utilize convolution as the main operation. Some nonlinearity is more tailored to modern convolutional neural networks. How pooling and max pooling, average pooling, these types of layers help us to make our networks more shift invariant. We saw how we can build classifiers using convolutional neural networks, and how that can be extended to other tasks. We saw some ways of visualizing what the neural network learns in order to understand what happens inside the convolutional neural network. And we saw some training considerations and some strategies that complement what we saw in the previous lecture, like dropout, data augmentation, patch normalization. And we also saw that transfer learning is a very popular and a very important technique, especially when we don't have a lot of data and we need to use more general classifiers to help us with the classification.